Hi and good day to everyone. We are creators group 8 from section 3. So for this chemical reaction mini plant reactor design challenge, the reaction that we choose is combustion of methane. In this team, we have Zhiyang, Baoyu, me, Chiho, Izni, and also Fihat. So as you can see here, the chemical equation and also the methane combust in the presence of oxygen to release energy. And also it is a highly exothermic reaction, and the conversion of methane to energy through combustion consider green alternatives, carbon capture and utilization (CCU). So the objective of this reaction is to use methane combustion efficiently for energy production while reducing CO2 emissions through innovations in reactor design and process optimization. Why we choose methane? Because methane is a primary component of natural gas and it is widely available. Although it is not renewable, but it is a cleaner burning fuel compared to coal or oil, producing less CO2 per unit of energy. And also with carbon capture technologies, it can contribute to greener energy system. Okay, now I'm explaining what is CCU, carbon capture and utilization. CCU is a range of applications through which CO2 is captured and used either directly or indirectly in various products. And CO2 is today primarily used in fertilizer industry or for enhanced oil recovery. Okay, so now we come to the reason of choosing plug flow reactor. So the first one, plug flow reactor allows for continuous operation and also critical for large scale energy production. It also offers high conversion rates, easily scaled to industrial applications, making it ideal for power plants or chemical processing units. And also the PFR design allow uh, efficient heat transfer and prevents overheating. So why do we not using CSTR or batch reactors? Because CSTR has lower conversion per unit volume and also higher operational complexity for combustion reactions. For reactors, it is unsuitable for continuous energy production due to start-stop inefficiencies.
Next, move on to our chemical plant design. This is a list of operating units. First, we have a mixer to mix the methane gas and air. Then, there will be a furnace to preheat the gas mixture. The temperature needed for combustion of methane is really high. Hence, to improve the efficiencies of the combustion, we preheat the gas mixture. After the combustion of methane, we use a cooler to cool down the temperature of the product produced. To separate the H2O gas from the gas mixture, we use a heat exchanger to convert the H2O gas into H2O liquid. Then a knockout drum is used to separate the H2O liquid from the gas mixture. Lastly, the absorber is used to separate the CO2 from the gas mixture. So this is our process flow diagram. The methane gas and air flow into the mixer at 298 Kelvin and 1 atm. In the furnace, the gas mixture is preheated to 623 Kelvin before entering the reactor. The temperature needed for combustion of methane gas is 2222 Kelvin. For the heat exchanger, we use a counterflow heat exchanger. This counterflow heat exchanger will improve the efficiencies of the heat exchanger. The temperature of the hot stream in a heat exchanger is lowered to 353 Kelvin to convert H2O gas into H2O liquid. Then we have a knockout drum and absorber to separate the H2O liquid and gas mixture. Next, this is the AutoCAD drawing for our chemical plant design. And that's all for our chemical plant design.
So for the simulation part, our group is using the MATLAB to model the methane combustion in a plug flow reactor PFR. So at first, we will define the constants first in order for us to calculate the rate constant K. So after we have get the rate constant K, we can calculate the rate of reaction, which is the R, and the initial concentration range for the methane and the oxygen gas is we already set in the MATLAB coding. After that, we calculate the flow rate and we insert the operating conditions for the temperature, and we assume that it is isothermal. And after that, we will run our reaction model, which is the PFR. So the second slide is about the MATLAB coding that we are using to calculate the flow rates and in the initial concentration with the respective coding. And in order us to calculate the initial concentration and the flow rate, and we also insert the ordinary differential equation for the PFR in order to solve and get the reaction rate. After that, we can get the final concentration of methane gas and oxygen gas, and also the conversion of the methane gas as requested by the question. And last but not least is the carbon dioxide productions over the methane gas reacted in the reactor. So this is the last slide that we are using the MATLAB coding. And this slide is we use the coding to plot two graphs. The first is the conversion of methane gas as a function of flow rate and initial concentration. The second is the plot of carbon dioxide production over the methane gas production. And as you can see in the slide, this is the first graph, which is the graph of methane conversion versus the flow rate and the initial methane gas concentration. So the conversion of methane decreases with the increasing of the flow rate, because in the plug flow reactor, the conversion of methane is directly linked to the residence time of the reactants in the reactor. As the flow rate increases, which means we have a higher flow rate, the residence time decreases, meaning that the reactants spend less time in the reactor. This reduces the residence time, allows the less time for the reaction to process, resulting in the low concentration of methane gas. The second graph is the graph of carbon dioxide production versus the flow rate and the initial concentration of the methane gas. So as we can see in the graph, the carbon dioxide production reflects the impact of flow rate and the initial concentrations. The production of carbon dioxide is depend on the conversion of methane gas. This is the first, and I can justify that if the conversion of the methane gas is low due to the high flow rates, so less methane gas will react, and this will lead to lower carbon dioxide production. The second affects the production of carbon dioxide gas is the initial concentration of the methane gas, because lower initial concentration of methane gas, it provides less reactant, which can lead to the less yield of the carbon dioxide gas.
So now I will present about the impact of Sustainable Development Goals. So first we have SDG number 7, which is affordable and clean energy. So we know that it will produce fewer pollutant than alcohol and oil. So it will make it more cleaner and cleaner choice for fossil fuel option to generate the electricity, heating or transportation. Besides, it also can act as a transition fuel for renewable energy, which is it can improve the energy access in location which is not fully established yet. Next, we have SDG number 9, which is industry, innovation, and infrastructure. So, we know that the methane combustion technology such as high efficiency gas turbine and advanced combustion engine will drive in terms of innovation in energy system. So this will emerge as a technology like CCS, which is carbon capture and storage, can be integrated with our power plant design in term to reduce the CO2 emission. So next we have SDG number 12, which is responsible consumption and production. So in this SDG number 12, we'll be focused more on ensuring the sustainable consumption and production pattern to reduce resources depletion, environment degradation, and pollutant. And it also can optimize such as the heat recovery and the CO2 scrubbing will play a critical role to achieve this goal by enhance the efficiency, minimizing waste, and reduce environmental impact. And lastly, we have SDG number 13, which is climate action. So we know that methane primarily in the form of natural gas. So it will be produce significantly fewer greenhouse gas emission compared to coal when we use it as a fuel. So the combustion of it will be approximately around 50 to 60% less carbon compared to other sources. So So we know that methane also can burn more efficiently, and it will be contribute to lower emission of SO2, which is sulfur dioxide, and nitrogen oxide, NO. So we know that this will make methane uh, as a transitional fuel towards decarbonization.
The last part is the impact of manipulating input parameters. The first is methane concentration. Higher concentration of methane may lead to a better net energy output, but it will require precise oxygen control to avoid incomplete combustion. The next one is flow rate. When we increasing the flow rate, it will shorten residence times, but which might reduce the combustion efficiency. But when we lowering the flow rates, it can improve conversion, but it will reduce the throughput. And the last one is air to fuel ratio, or AFR. Optimal AFR will ensure complete combustion and maximum the energy efficiency. But excess air will reduce the efficiency, while insufficient air will causes unburned methane. So that's all from us. Thank you.